Hello everyone, I just got off from the plane and I'm currently at KKIA. I'm waiting for Imago to open up. It's still very early in the morning, so while we wait, let's see the mechanism of nitration of benzene. In this reaction, we will involve nitrobenzene with concentrated HNO3 to form metadinitrobenzene and water. But before we dive deeper into the mechanism itself, when the question asks us to draw the equation of nitration of benzene, don't forget to write the detail over here. On top of the arrow, we must write the catalyst of the reaction, which is concentrated H2SO4, and under the arrow we need to write the specific temperature of the reaction, which is 50 degrees to 55 degrees Celsius. Okay, for the first step is the formation of electrophile. If you are confused or cannot remember how to start this mechanism, remember that for this first step, it will involve this reactant and catalyst. Involve this. Okay, so copy back these two things in its expanded form. So now, this H atom is more electropositive and this oxygen atom is more electronegative. This lone pair over here is attracted to the more electropositive H atom. So we need to draw an arrow of it attacking this H atom. You can draw a prettier arrow than that. Okay, when this lone pair have taken custody of this H atom, this sigma bond between the H atom and the oxygen atom will break. So the two electrons over here will be pushed to the oxygen atom because it's more electronegative, can hold the electron better. Copy back the expanded HNO3, but the lone pair over here will be replaced with the H atom. And since the oxygen here has lost its lone pair, it will be more positive. And then the H2SO4, the H here will be replaced by a double bond. And since the oxygen atom have a lot of lone pair now, it will be more negative. Alright, is this a good enough electrophile? No, not yet. There's this term in BM, orang tamak selalu rugi. This greedy as oxygen have taken custody of this H, and when it has taken this H, the sigma bond between this oxygen and this nitrogen will become weaker, and the sigma bond between this oxygen and nitrogen will break, and the two electrons over here will move to the oxygen. And when well, thank you, man. Okay. So the two electrons here will form a double bond, and this will break them, forming a water molecule and nitronium ion. It is a much better electrophile. And this ion over here, just copy and paste. Very easy. Now moving to the second step, and for me the most difficult step, is the formation of rhenium ions. Rhenium ions might be a new term for us, but we'll manage. So this benzene ring acts as a nucleophile because of its delocalized pi electron cloud. The electron-rich benzene is attracted to this poor and electrophilic nitronium ion. For this reaction, you can choose whatever double bond that is not occupied by any alkyl group. For this one we cannot use this double bond for the reaction because it has already have a nitrile over here. You don't exactly kick someone out of their own house, do you? So we can use either this or this, but I'll choose this one because, well, it's closer to the reactant over here. It's much easier for me to draw the arrow. So the 2 pi electron over here is pushed to the electrophile, like so. You can draw a better arrow than that. Since this benzene ring, like any other aromatic compound, it is very stable because of its delocalized pi electron cloud. So it takes a lot of energy for it to break the double bond. And to indicate the slowness of that reaction, we need to write slow on top of the arrow here. Now to the most difficult step for me to understand is the rhenium ions. You might be confused. Why is there suddenly 3 benzene rings? Did you just pull a Boy Trinity or something? Nah. Man, chill. So, I don't exactly remember the exact definition of this rhenium ion, but in my understanding, rhenium ions is like an animation frame representing the delocalization of the positive charge of the carbon. Because you see, when we break the double bond over here, of course, this one end will attach the nitrile ion over here and a H, and then the one left behind will have a positive charge. Okay, so copy back the double bond that is not bothered earlier, like so. For us to represent the delocalization of the charge, we should draw an arrow anti-clockwise to show it moving, like that of some sort. Okay, this will move first, and then you draw the second one. The bond will be here, and this one will be like, hey, wait for me, and then draw an arrow of it moving over there. Oh, and the charge from here will move here. Why not here? Because there's things in this. It will move here. It's a very polite charge. So, and then write the double bond moving there, and then the charge will move over there. I hope you understand what I'm trying to explain. It's very hard to explain in the professional term. Okay. Moving on. The audacity of these buses, man. Jeez. Okay, for the third step, the deprotonation of rhenium ions, copy back this first rhenium ion for your reaction. Boom, like that. Okay, usually the H atom and the positive carbon is next to each other for this reaction. Okay, there will probably be like a standardized term to explain this, but I'll try to explain it in the way I understand. This ion over here, that's from the catalyst, have come for revenge. It wants to reclaim the H atom over here. So the negative charge will move to this H atom, and then the H2SO4 will be reformed back to its normal state. So now this negative charge that have switched places here will form a double bond, which makes the benzene ring stable again. It restores its aromaticity. So draw the double bond over here, and there you have it. Methyl dinitrobenzene is formed. So the reaction of the mechanism of nitration of benzene is complete. I'll enjoy my day at Imago. Goodbye.